Lesson 6-2, Solving Systems Using Substitution. Alright, systems of equations can be solved in more than one way. When a system has at least one equation that can be solved quickly for a variable, the systems can be solved efficiently using substitution. Basically, in our last lesson, 6-1, we learned that if we have a system of equations or two graphed lines, we can graph them and find the point of intersection or points of intersection to solve for the solution of the system and get that xy value. The second method we can use that we're learning today is called substitution. Basically, if you have two equations just like we did in the last lesson, if we set one of them equal to a variable, in other words, y equals 3x, we can substitute that equation or value for y into the other equation and find our xy solution. Here's what I mean. This first equation is already done for us, y equals 3x. So I'm going to start with this second equation, x plus y equals negative 32, and wherever I see a y, I'm going to substitute 3x. So rewriting, x plus 3x, because that's what my y equals negative 32. X plus 3x is 4x. Divide both sides by 4, x equals negative 8. So we just found our x value of our ordered pair, or the solution to this system. To find the y value, I'm going to plug negative 8, my x value, into either of these equations. I'm going to use the first one because it's shorter. So y equals 3x. I now know that x is negative 8. Times that by 3, I should get my y. Y equals negative 24. There is our xy solution for this system of equations. Now, negative 8 and negative 24, we can still, just like the last lesson, put this solution into both equations to check that it works. And you can see, plugging negative 24, negative 8, negative 24, negative 8 into both of the equations, they each work. So we know that this is the correct solution. Alright, like I mentioned earlier, to use this substitution method, and it's very handy, you have to have one of the equations be solved for a variable. In other words, in the last example, we had y equals something. Neither of these equations are set up for a variable, so I need to make one of them be y equals or x equals. So I'm going to use this second equation, negative 2x plus y equals negative 3. If I want to solve that for y, I'm going to add the 2x over. You want to pick the equation that's easiest to solve for the variable y. It'll save you work in the end. So I added 2x over. That's my final equation. Now I can use this first equation, 3y plus 4x equals 14. Wherever I see a y, I'm going to plug 2x minus 3 in. So right here, this y, 3 times, I'm going to use this, 2x minus 3 plus 4x equals 14. I have to do a little distributing. 3 times 2x, 6x minus 9 plus 4x equals 14. 6x plus 4x is 10x. Negative 9, if I add it over 14 plus 9, sorry, just checking my work, is 23. Divide by 10, x is going to equal 2.3. Oops. Sorry. X is going to equal 2.3. That is the x value of our solution. To find the y value, I need to plug that x value into either of the equations. I'm going to use the first one. So 3y plus 4 times 2.3 equals 14. When I do the math, I get y equals 1.6. So my solution to this system, using substitution, is 2.3 for x, 1.6 for y. All right, now we're going to use a real-world problem to use substitution in order to find our solution. A snack bar sells two sizes of snack packs. A large snack pack is $5 and a small snack pack is $3. In one day, the snack bar sold 60 snack packs. So we're going to have two equations. One of them, we have a large snack pack and a Y snack pack, and on a certain day, we sold 60. Now, a little bit more specific, if we keep reading, we made a total of $220. The large snack pack is $5. So 5 times my large one plus 3 times my small one should give us a value of $220. How many small snack packs? How many small snack packs did the snack bar sell? So we want to know our Y value. Okay, so to do this, I'm going to use substitution. This first equation looks really simple to solve for a variable. I'm going to say y equals, subtract my x over, and there I have it. So now I'm going to substitute this portion, whatever the y equals, into this equation wherever I see a y. Get rid of that arrow. Okay, so here we go. 5x plus 3 times, here's my y, negative x plus 60 equals 220. 5x plus 180 minus 3x equals 220. 5x minus 3x is 2x. If I subtract my 180, I get 40. Divided by 2, x equals 20. So right now, we know our solution to this equation. X is 20, meaning we sold 20 large snack packs. Now to find y, because they want to know about the small ones, which we labeled with y, we need to put 20 into our equation. I'm going to use this one. 20 for x plus y equals 60. If I subtract 20, y equals 40. 2040 is the solution. To answer the question, we sold 40 small snack packs. All right. Now we talked about how some systems have infinitely many solutions, or they can have no solution, meaning the lines do not intersect at all. If they have infinitely many, the two equations are the same line. So I'm going to show you what this is going to look like when you're using the substitution method. It's really easy when graphing, but what about substitution? All right, here we go. So just looking at A. All right, looks like this equation is already set equal to a variable, x equals something, so I can plug it right in. 3.5, wherever I see x, I'm putting in what x equals. Negative 2y plus 4 plus 7y equals 14. When I do the simplifying, negative 7y plus 14 plus 7y equals 14. Notice here that if I subtract the 14 from both sides, I get 0, and this one cancels, and negative 7y plus 7y also equals 0. When you substitute an equation into another equation and your variables are eliminated and you have two numbers that are set equal to each other and they're the same number, this system has infinitely many solutions. Whereas, example B, looks like one of the equations is already set equal to a variable, so I'm going to plug 3x minus 11 into the second equation wherever I see y. So here we go. 3x minus 11 minus 3x equals negative 13. Well, 3x minus 3x cancels out. I'm left with negative 11 equaling negative 13. In this case, when your variables disappear from the equation and you're left with two numbers set equal to each other, but those numbers do not equal each other, this system has no solutions. All right, that ends the examples for Lesson 6-2. Please complete 1 through 5 of the lesson check and bring your answers to class.